So the next, we're going to go into section 2, starting with question 1. It's a truss. Now, it should not have been a surprise to anyone that trusses are going to be in an exam. Trusses will be in every exam, right? If I haven't made that somehow managed to skip past you and you didn't pick up that trusses are going to be in every exam. Let me just say that again. Trusses are going to be in every exam. So the first thing you have to do is you have to be able to find reactions. So when we're finding reactions, we usually want to find find the roller first, which means we take moments about the pin. So in this case, we're going to do sum of the moments clockwise about which location is the pin? B is the pin, equals 0. So starting from 0, we have reaction B, and it is how far away? 0. So it doesn't have any turning force. There's only two other forces on this truss, right? We have our, 3 kilonewton force?
3 kilonewtons.
So I'm writing minus 3 for 3 kilonewtons. How far away is it?
Its perpendicular distance is 4.5 meters.
Exactly right. I'm going to write it as 1.5 plus 3, and then I'll write 4.5 above that, just to help me understand where I'm going. Is that going clockwise or anti-clockwise? If I put a pin on B and twist it, yeah, clockwise, that's right. So I'm going to turn that minus sign to a plus. Now I have minus reaction A. Now, what distance away is that?
8.66.
Okay, the perpendicular distance from reaction A? Okay, so it did require you to do some thought, right? Yeah, 2.66 is the answer. So what we have is we have an equilateral triangle that's 3, 3, and 3. Yeah?
Okay.
An equilateral triangle 3, 3, and 3. If I cut that in half, now I have a triangle that is 1.5 and a 60-30 triangle. Okay. Now, if I know this is the hypotenuse is 3, and I want to find the opposite angle, right? Or if I want to find the opposite angle, what will that be? That'll be 3 sine 60, which equals what? 3 sine 60 is the same as saying 3 times 0.866, which is equal to what? 2.66. Right? So 2.66 meters. Now I can write that in there as 3 sine 60, and that's fine. And I'm just going to write above that 2.66. Okay. Now I just apply that out. So what I'm going to get, the 0 will become 0 equals 0 minus 3 times 4.5 is what? 13 and a half, I think. Can someone type that into a calculator? Come on, guys. Yeah. Sergey?
What is it?
3 times 4.5?
13.5.
Thank you. Okay, 13.5, so it's plus 13.5 minus 2.66 RA. Okay, I'm going to move the RA over here. I don't need to do that any special stuff. Everyone knows how to do that, right? 2.66 RA, right? I'm adding RA to both sides. Gives me 13.5. So RA, if 2.5 RAs, if 2.5 RAs cost me 13.5, how much does 1 RA cost? About 5. Yeah, okay, so how much was it exactly? Is it exactly 5?
5.0751.
5.07. Okay, 5.079, you say?
5.075.
Yeah, so it rounds up. 5.08. Okay, kilonewtons. Now, it's important to say our assumption was that Ra was going anti-clockwise. The number was positive, therefore our assumption was okay. Yeah, so I'm going to write that here. RA, we assumed it was going anti-clockwise, therefore negative. Right, here the answer was positive. Right, I can write it even here, positive. Therefore, our assumption was okay. Right? Therefore, it's going that way. Okay, we found RA. RA was pretty easy. Okay, so now we've got to find RB. To find RB, right, we're going to use our sum of the forces vertically and horizontally. So sum of the forces vertically, well, sum of the forces vertically equals 0, therefore RA is going to equal RBV. Right? Oh, sorry. If we start vertically, so we're going to start off with RBV rather. RBV equals 3 kilonewtons up. Now, I would even find that hard to write anything more than that. What I would do is I would just draw 3 down and 3 as RBV. Yeah, I would just do that. Okay, as for sum of the forces horizontally, well, the only two forces are those reactions. So same thing. 0 equals, well, we've got 2.6 going this way. RBH equals 2.6. So if RA is pushing out, if RA is pushing out to the right, which way is RBH going? If RA is going out into the right, so RBH has to be going to the left in order to counter that. Yeah, I like to draw my pictures, as you know. So if RA is going this way, RBH has to be going that way, 2.6 kilonewtons. Okay, so now we just do our Pythagoras' theorem. We say that if it's going this way and that way, we've got 3 and 2.66. Not sure it's not as good as it could be. What is my reaction going to be? RB is going to equal what? It's going to equal 3 squared plus 2.66 squared equals what? Come on guys, you guys got calculators? Go. Come on, what's the value of RB?
I can't even see.
4.0.
I need to get my glasses on for this.
4.00. Yep. Okay. Okay. Kilonewtons. And what's our direction? What's our value of theta? Theta equals tan opposite over adjacent.
So why are you using 2.6?
Because what's our value of RA?
Alright.
Oh, RA was 5.08.
Yeah.
Thank you for helping me out, guys.
Oh, fuck it. I'm trying to read.
Wait, what's that?
Okay, sorry about that.
That's
Surround.
5.89.
5.89.
Yeah.
And what's the angle? So we've got opposite over adjacent, so it's going to be 3 over 5.89. Sorry, 5.08.
That's equal to 30.56.
Now, guys, it's important at this point to say, does that number seem sensible? If this is 5, wait, if that's 5, and that's 3, does that angle look like it's about right?
Yeah.
Does that number look about right? Yeah? Okay. So that's our reactions. Now, what's 90 seconds? What's 90 seconds times 3 minutes? Guys, what's 90 seconds times 3 minutes?
540 seconds.
Okay, so how many minutes do you have?
So,
9.
Okay.
Yeah.
It shouldn't be more than 6. It should be about 4.5.
We'll do it again. What was the question?
You got 90 seconds per mark. It's a 3-mark question.
90 seconds.
Legally, that is. Yeah, he's gonna have it on profile.
Yeah,
Okay.
4.5, so.
Now, Max, you were moved because you were talking. Yeah? Okay. So, we've got our reaction. How many minutes do you get? 4.5? 4.5 minutes. That sounds about right. Okay, so you had 4.5 minutes to do that. Now, obviously, I take longer because I'm writing in giant font, and I'm explaining everything as I do it. But the goal is here that you should be able to answer a question. That was a particularly easy question too. There was only one external force. Yeah? Now, for part B of this question's 5 marks. That means you've got 7.5 minutes to do this. Now, I think I'm pretty confident I can answer this in less than 7.5 minutes, right? But let's see how we go. Okay, so what we're going to do now is we're going to find members B, C, and CE. Members B, C, and CE.
It's 10:25. You've got 8 minutes until 10:33.
Okay. So, guys, I'm not going to stop because I'm being timed. I have to find CE, and what was the other one? BC. Okay, so I have to find this member and that member. So what I'm going to do is I'm going to draw a version of that truss that cuts through both of those. So I'm going to draw this like that. Okay, BC, CE, and DE. I have one external force, 3 kilonewtons down. Okay, if I want to find CE, what I want to do is I want to take the sum of the moments about a point where I can eliminate two things. So if I look at CE, where does CE and DE meet? They don't. So I have to use some of the forces vertically instead. I need to have the lone wolf method. Only one man is man enough to do it, and it's CE. So I've got some of the forces vertically. I've got 3 going down, and then I've got up. It's going to have to be the CE vertical component, which means that CE is going to have to be going that way at 30 degrees or 60 degrees. So I can say CEV equals 3, therefore CE equals something bigger than 3, right? So I'm going to say CE equals 3 divided by 0.866. Which, can someone do the calculator for me? Okay, I'm going to start moving on, and then I'm going to say the sum of the moments to find BC, which is the next one I need to find. If I want to find BC, I need to eliminate these two. Where do they meet? CE and DE, the clue is in the name, they meet at E, that's right. Okay, so they meet at E.
To your previous one is 3.46.
3.46?
Yeah.
I knew it had to be bigger than 3, so that's good, okay? And so it's going to be going in this direction. Because I know it's going in this direction, it makes a letter C. It's going into the node, yeah? When we pull out of the node, we're in tension. If we're not pulling into the node, if we're not pulling out, then we're something starting with C, compression, right? So it's compression. Okay, to keep going with my sum of the moments, I'm taking sum of the moments about E because I know that that's where they meet up. So I can ignore these two. So I've got BC. How far away is BC? I know that BC is 2.66 away. I know that because I did that last question. How far away is the 3 force? The 3 force is 3 meters away. Which of these are clockwise? BC, if we're assuming tension, BC is anti-clockwise. If we're assuming clockwise, BC is anti-clockwise. If we're assuming this one is positive because it's going clockwise, so 3 times 3 is going to be positive. That means if we move this over here, we have 2.6 BC equals 9. Right? I can do that 3 times 3 in my head. So if I have 2.6, let's say if I had 3 BCs, I know, and they cost me $9, I know that each of them are going to be about $3. So BC is going to be a little bit more than 3 point something. How much? 3.46. 3.46. It's positive, therefore my assumption was correct, therefore it's in tension. Don't forget the newtons. Bam. How'd it go?
That's right.
No, with time?
Yeah.
You have 5 minutes.
Yeah, great. Cheers.
So,
Okay.
sorry. Just going back to it, it's not actually 2.66, it's just 2.6.
We're gonna live with it.
Yeah.
Right? We're gonna live with that. Even okay, in that situation, that's a good question, right? Would a marker would a marker take marks off there? I think that there's a certain. I'm pretty sure that they look. Here's what I would do. I've never done HSC marking. It's a good question. I will ask people who have done marking. But my attitude is that if you have shown your working out, you've shown how you've done your calculations, I think that as long as we're within a reasonable margin of error, you'll be okay. Now, the worst case is you'll lose 1 mark, right, out of the 7 because of 1 continued carried error. But even then, I think that as long as you've shown your working out and it's within a reasonable margin of error. Now, the reasonable margin of error is really important here. That's why I always ask, does this seem reasonable? Yeah, does this seem reasonable, like what you've done is reasonable? I think that people would look at that and say, when I've done my marking for you guys, I've looked at it and said, yeah, look, as long as it's within, say, 10%, I'm pretty much happy because I know that people are going to use different rounding and they're going to use different values. Now, in actual professional engineering, like I said, 2% matters, right? If you're out by 2% all the time, if you're 2% over every time, people will stop hiring you because 2% matters when you know the cost of all of your materials is 2% higher. That's enough that people will go to someone else. People will go to other suppliers for that sort of margin. Okay, but there was a lot. I did that fairly quickly. I didn't explain it to the extent that I normally explain trusses. If you'd like, I'm happy to go through this a whole second time to go through it. Or what we could do is, I think the best thing, at the end of this exam, I get someone up here and they get them to do it. Someone who isn't feeling super confident about trusses. Yeah, I think that's probably the best way to do it, is we go through it again at the end of the lesson. Okay. I'm saying that now because otherwise I'll forget.
So if I could go to
Okay. Okay, so now we've got written questions. These are good because I don't have to stand up. I can just talk into the mic now. Okay. 22A. Identify one example of how bridges have benefited from technology advancement. Hit me with it, guys. Give me an example.
Alloys have led to stronger bridges.
Great, that's a really good answer. Yeah, you could talk about alloys. You could just even talk about the development of steel, but alloys is great. Yep. Anyone else?
We should do more of these pages. I like this.
Come on, someone else has got to have something. Look at the bridges on the wall, at the very least. So we've talked about material advances. What's an alternative to material advances?
length advances.
How? How did we achieve longer bridges? Once upon a time, we used to have trees that fell down and crossed rivers. Right? Freddie, give me an example. What's a way that we now can cross bridges longer than logs across rivers?
We have steel.
Great. Steel. We've already talked about alloys. Give me something else.
Supports. I don't know.
Look at the wall behind you for inspiration.
There's cantilevers.
Cantilever bridges. Yeah, okay. That's a different design technology. Yeah, what's a different, aside from cantilevers, someone else give me another one. Arch bridges. Great. Arches are good because you can use stone.
Girders.
What's the advantage of stone?
Good in compression.
Yeah, it's good in compression, but also it's really durable. What's durability? My year 11s didn't know what durability was. Well, no, that's hardness. Durability is it lasts a long time. It's not flammable. It doesn't corrode. It's not biodegradable. You compare stone to wood. Well, no, you compare stone to wood, right? It doesn't rot. It doesn't decompose. It doesn't burn. It doesn't wear away. It doesn't rust. Yeah, stone can last a really long time. It does erode, yes, but it takes a really long time for it to erode. So it's very durable. That's the advantage of arches. You can't build a bridge out of stone unless you have arches. So that's where the arch design allowed for that. Okay, Divin, give me an example. What's a difference? Freddie's already talked about box girders. Give me another kind of bridge. Look at the wall. Starts with an S.
Span.
Sydney Opera House is interesting. It's a arch bridge. It's a truss bridge. Yeah. So I've just said a word that starts with T. We just did one a second ago. They look like this. Trusses. Okay, what's another one? Starts with S. Suspension. Yeah, so these are all answers you could have given. Yeah, changes to the design, changes to materials, right? Also, advances in our understanding. Yeah, finite element analysis, things like computer-aided design. They've all helped greater quality control. They're answers that we could give. Okay. Describe an environmental advantage of public transport compared to private vehicles.
It uses less fossil fuels.
Okay.
Per person.
Per person. That is the key to the second mark there.
In turn, there's less pollution.
Yeah, great. So yes, less pollution per person is really the important part. Yeah, you need to kind of spell things out for the second mark. Okay, why is that an advantage?
Less pollution means less ice caps melting, which means
Great. Yep. Contributing to global warming, climate change. Yeah.
I'm sure I actually read less polar bears dying in my paper.
Okay. So less pollution, which means less climate change. It also means better air quality, right? Reduces respiratory problems. It also means less dependence on non-renewable fossil fuels, which means we have something for future generations to use. Yeah? These are all environmental advantages. When we talk about the environment, it's not enough to say, yeah, look, using less petrol is good. You have to say why using less petrol is good. Yeah? You could talk about there's an economic benefit of using less petrol, but more importantly than that, you can say we're not using this non-renewable resource, which means we have more for other people. We're not putting poisonous gases into the air, and we're not contributing to climate change. Okay. Describe a social influence that has contributed to the development of transport. Now, this is a social influence. An influence is something that has led to engineers and engineering doing things. What is something that has happened in our society that has made people more likely to use to develop transport? Yeah.
The need to travel longer distances.
Okay. How has that developed our transport?
Well, we needed to make things that could travel them distances, so better than legs.
More efficient, faster transport.
Okay, look, that's an interesting answer. The need to travel longer distances has led to people developing things like the railway, right? Yeah. So that people can actually cross those distances or in a faster time. I think that saying something about time or the fact that the manpower improve quality of life is great. Yes, okay. Or imagine how we used to transport steel before we had railways. Yeah, like on the back of carts. Yeah, horse and carts. That's how we used to transport it. So there's an economic need there, right? People need that steel faster and cheaper. Yeah, or used to send it before the railway. Used to put it on canal boats. People would build canals just so that we could transport things on water. Okay. So someone give me something else. One I think you should always consider is racing. Yeah? Racing. People like racing. Racing has led to huge increases in sport. Right? They've led to a huge... so they've led to huge developments in fuel efficiency, power, control. And then the next big one is demands for safety. Now, I posted for you guys the Nut Behind the Wheel, a 99% Invisible episode, about how in the 60s people didn't consider car accidents to be a car design problem. They considered it to be a human problem, a driver problem. The video actually the podcast goes on to draw the link between guns don't kill people, people kill people. People used to say cars don't kill people, people kill people. And then this guy who was a fighter pilot who survived a crash landing, he started looking at what are the things that we can do to make our design better to prevent deaths. And so companies like Volvo, they made their brand based around the fact that our car is safer than every other car. If you buy our car, you're going to be less likely to be injured by this car. Yeah? So up until then, before things were like Renault is famous for introducing the seatbelt, right? Things like the airbag, things like the collapsible. Really important design innovation is the collapsible steering wheel. These are all important things. I've talked about this. I know I've talked about this because I posted the Nut Behind the Wheel episode for you on Facebook. So there are lots of answers there. Okay. Structural timber beams are often laminated rather than being one solid piece of timber. Outline 2 structural advantages of using laminated beams for long spans in building structures.
We don't have
Not in the test.
Really?
Yeah. We explain one reason why referencing is important to engineering reports.
I really wanted to put this question in, and I decided, nah, look, I just didn't fit, didn't have the marks for it. What was I going to cut? And I thought, nah, I'll leave it. So this might be for future generations. I might have to edit this question so that way I can't, as a nice surprise. See how it went onto another page? I didn't like that. Okay. Explain one reason why referencing is important in engineering reports.
So you don't get sued.
Yeah, that's an interesting answer, but you need to explain that. Why might you get sued?
For taking someone else's work.
Oh, okay. So plagiarism. Yeah. I don't know if anyone actually sues people for plagiarism. It must happen.
Well, it must happen somewhere.
I think what it usually is just professional
Not like
reputation.
people who plagiarise all the time.
Well, I think what it is it's the damage to your reputation is why people don't plagiarize. Yeah, that you look like a fool professionally and you lose a lot of your credit. Okay, yeah, but we don't like plagiarism. Yeah, that's one reason. Yeah, it's not really the most important reason. Okay, Max, you need to stand up and you need to come over here.
So we're just talking about this.
I don't care. Okay. That Buns, what a jerk. He doesn't even let me discuss the exam. It's like he doesn't want me to learn. But while you're talking, it's distracting other people. It's preventing other people's ability to learn. Yeah? While you're talking, you're not hearing this valuable information that I'm giving to you for free. For free, I'm just chucking it out there. Well, not for
It's
free.
not really
Someone's...
for free because you pay for our taxes.
That's right.
Yeah,
That's
pay
exactly
for it,
right. Yes.
so-
Okay. Yes. Good reply to that. Okay.
That's like
So, Freddie said you don't want to get sued. What's another reason why we put references in? Go.
To document where information came from.
Good answer.
Error or it needed to be found again.
Excellent. That's exactly right. Yes. That extra part there was really important. Yeah, where information came from, that's good. But why? In case there's an error or in case someone wants to fact check. Someone wants to go back to that original source. Yeah, someone wants to find and check the validity of that. That's really important. Okay. That's pretty much what I'm going to go with. I had something else, but I've forgotten it. Okay. Why do engineers work collaboratively? Now, I just want to point out this keyword here is explain. When you see explain, that means I want to see a cause and effect. Yeah? What's the cause and effect?
Having more engineers means the skill pool is larger.
Yeah, okay. That's right. So these days we become more and more specialized. People become more and more specialized in certain fields. So people can know more about that. They can have a deeper knowledge and we can have better understanding from those experts. And working together, we were able to share that expertise. That's one answer. Yeah, what else?
having more engineers on the same piece of work reduces the likelihood of an individual mistake occurring.
Excellent. Verification and validation. Yeah, so that having more people on site means we're less likely to have problems. That's great. What's another one? If I want to build a bridge, could you imagine if I wanted to build a bridge, right? When I build a Sydney Harbour Bridge, it's just going to be me. Just me, yeah? Right? Now, I have all the skills, unlike Freddie, where, Freddie only knows some of the things, like how to drive a crane or how to, work with steel, right? Yeah, okay. Me, I don't know how to do all of these things, right? I'm just going to do it on my own. I'm just going to build the Sydney Harbour Bridge on my own. What might be a problem with that?
It's
Terribly
It's
efficient.
a lot of workload.
Okay, it's efficiency, right? We can get more work done. If anything, we actually get it done faster than if we just had one person, right? When I used to work in renovations, right? When I was in building, I mostly did renovations, and I always worked with one other guy. And that guy had told me how he'd had times where he'd gone on jobs and said, no, I don't want to pay for two people. And it's like, but we physically couldn't do this job without two people. Like, we couldn't carry the timber. We couldn't. If you have someone driving the crane, you need someone at the bottom of the crane.
It would also probably cost less to do it with two people because you're taking less
Do it
time.
twice as fast.
Yeah, you have reduced.
Probably more than twice as fast. You do it more than twice as
That's
fast.
right. You have reduced overheads. You have reduced interest rates. You have a whole bunch of different advantages. Okay, so efficiency, right? Specialization, reduced mistakes. Okay, there's one other one that I want to look for. What's someone who does DT should be? This really should be in your ballpark. Is there anyone left?
Yeah.
Is he asleep? No.
I'm
Yeah. Okay.
DT. Do you want me to just read my answer?
Yeah. Go.
When engineers work in teams, more can be accomplished in far less time. There is an increase in efficiency and also problem solving as there are more minds put to work.
That is exactly the last half is the third part I wanted, right? You have better problem solving. The more people who are working on a job, the more people from different experiences and different walks of life, the more likely you are to not just prevent mistakes, but you're going to have better solutions. Yeah. So one of the reasons why we like to have multiple people working together, we like to have efficiency, we like to have specialization, we like to have better problem solving, and we want to have reduced mistakes. Okay, moving along. Okay, question 25. The following graph shows a tensile test on a metal sample. What kind of yield do we have, guys? Kitty from Progressive. Yeah, we can't see a definite yield point, so we have progressive yield. Yeah, definite yield point was where we have the like steel, where we have the little curve in there, and we can find a yield stress. Yeah. In this case, we don't have that. So, what do we use instead? If we don't have the yield stress, what do we find instead?
0.2%.
Proof stress. That's exactly right. 0.2%.
It's on the same gradient, isn't it?
That's right. So what we do is we draw this at the same gradient. So what I'm actually going to do is I'm going to move this over to the bottom of the screen so you guys can see.
Right, but they did the line.
Now, I think I actually drew for every one of you. I think I actually drew this line that I'm going to draw. But so whatever this gradient is here, if that's that gradient there, I just go across to 0.2%, yeah, 1/5 of 1%, and go, ooh, what a great time for that to die. And look,
That is miles off. I feel like it was like it was 125.
no, look, it's somewhere
It's
between.
under 150.
It's somewhere between those two.
Swear
Yeah.
I could have you at 125.
Look, this was actually a multiple choice question, and I'm pretty sure the answer was actually 140. But look, I would have accepted anything between 125 and 150 because
75. Can you cop that?
I better have a long look at that paper of yours, Freddie.
I've lost it.
Okay. Okay. So now the original one was a multiple choice. It did not tell you that the proof stress was 0.2%. I added that because I just wanted to be helpful. Devin, could you do me a favor and pull down that? Okay. Now, part B. Guys, part B asks. Part B asks, identify a hardness test suitable for the following. Thin metals? Vickers. Vickers for the thin metals, for the cat food. That's right, for the cat food test we use Vickers. Yeah? Okay, for on-site inspections, what do we use? The Shore scleroscope. Okay. You know what?
Don't just write Scott.
Yeah, that's right. If yeah, I was pretty flexible on terms there. Yeah, if for people giving answers. Obviously, it's written in the textbook. We've talked about it before, but
Wow, what a good time.
but what are the other two? How many times did I see the word Rockwell on that test? Lots of times I saw Rockwell. Okay,
Wow.
now
Could pick the captain.
okay, so Rockwell is a commonly used test. The problem is it's not ideal for thin metals. It's commonly used. It's a good one. We like it because we consider it to be non-destructive, right? The other one is the Brinell test. Now, Brinell is kind of like from the before time.
Brinell's the
It's
worst
just
version
rocks,
of Rockwell.
isn't it?
Yes, it's a worse version of Rockwell. That's right.
It's a steel ball
Actually-
instead of
Steel
no,
ball.
it's
Oh, right.
Sorry?
It's actually destructive.
Well, it's considered to be destructive. It leaves a big enough mark that it's considered to be destructive. Okay.
That one is stupid.
Now, thank you. Okay, for part C, explain the purpose of a slump test. Anyone?
Check Darcy hasn't thrown a bag of oranges in the
Let's
concrete.
check.
Okay.
There's no oranges in the concrete.
Yeah, I think I did actually see oranges written a couple of times. I don't even know who started that. It's not my thing. You guys embraced it.
You did it.
I refuse to
No,
believe.
you
I
said
re-
like
No, I think it was
you
You're
were
right,
doing a
it's
story of like
oranges
concrete
and
as in like some
Sylvia,
dude.
whatever.
Yeah,
So-
With oranges in the mix.
It was Spiro jumping the concrete and someone asked, oh, what would happen if you chucked an orange in
yeah,
it?
yeah. I think an orange or two you'd probably be okay, but I wouldn't do it. I wouldn't recommend it. I don't want to go on record on the recording here as say no oranges.
No.
I probably would have said at that time that I remember hearing that Snowy Mountain scheme that people had fallen in. I don't know if this is true or not. Someone can tell me, can fact check it. But people have fallen in and they just had to keep pumping because at that point you can't jackhammer out a section. You know that it's they just have to accept. I'm sorry, it's happened. Maybe it was the
That would
Three
suck.
Gorges.
Imagine if you were the one like on the pump. Like, oh shit, what
Yeah.
That's fine.
Anyway, I don't know if that was true of the Snowy Mountain scheme or maybe it was another bridge like Three Gorges or something like that. Anyway, what I wanted to talk about, okay, the slump test, the reason for the slump, if I said explain the reason for or justify the use of a slump test, I would have said to see if the concrete is workable, to see if the moisture content in the concrete was within acceptable working conditions. Yeah, to see if it was too wet would be another answer. The fact is, I asked for what is the purpose of the test. So why do we do the test?
Like to test the viscosity of concrete on site.
Yeah, to see if it's workable. That's right. Now, if I'd said I set up this wrong earlier, but I'm like, oh, the more I talk, the more I'm thinking like, probably should edit this. I'm now just gibbering. I'm just ranting. Just rant. I can't stop. Because I don't have free will. I just like my brain is just ah.
Jesus Christ.
Okay. If I said describe the slump test, what would I be looking for?
Put concrete in a cone and describe the process, like the method of it.
Put concrete in a steel cone. You use a rod to make sure it's worked in properly. And then you tip the cone upside down, and you look at how much the concrete has falls apart. You know, how much it slumps. You're right. You could even then talk about how if it shears, right? If it just slides off from the side, you have to redo it, right? But I asked for the purpose. The purpose is to see if it's workable. Now we talk about cause and effect. So when we talk about cause and effect, we say that if the slump test, if there's too much slump, we can't use the concrete. Yeah. If there's a little, if it's too dry, we just add more water to it. Yeah. Okay. Yeah. So it's so the purpose is we need the cause, we look at the results of the test, and then the effect is we decide whether or not we can use the concrete. Okay. Okay. Da 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 da. Da 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 da. We got a question about flea.
You don't realise what you've done, so
No.
Okay.
no.
So
Yeah, you haven't mentioned it.
the original gauge length of the steel test piece.
No, I've been here for 3 hours and I haven't eaten.
The original gauge length of the original gauge length of a steel test. The original gauge length of a steel test piece was 50 millimeters with a diameter of 8 millimeters. If the Young's modulus of the steel was 210 gigapascals, what is the expected extension of the piece under load, under 10 kilonewton load? Okay, so we've been asked to find the extension. So the formula is capital E equals FL over little e, capital A. Yeah? Now, the other way of writing it, so this is really just an expansion of the stress, Young's modulus, capital E. So why is it an E when it's Young's modulus? Come on, guys. It's Young's modulus of elasticity. E for the elasticity. The Young's modulus is a measure of elasticity. It's the gradient of the stress strain curve. Yeah? The straight part of that curve, it has a Young's modulus. And the Young's modulus of elasticity is its gradient. It is the Young's modulus equals stress over strain, which we can then rewrite as FL over EA. Now we can rearrange that that formula. So therefore E equals FL over EA, but this time we've swapped the E's. Right, I actually gave you an easy one, right? The easiest one is we can swap the E's with no effort. Yeah? Okay, so what are we going to find? Well, we've got F. What's our force? 10,000 newtons. Okay. Times what's our length? 50 millimeters. Okay. What's our Young's modulus of elasticity? 210,000. That's right, because a gigapascal is 1,000 megapascals. And what units do we use? SI units and Greece units, because we go together like megapascals and millimeters squared. Okay. And then for our area, well, I'm going to do pi d/4, right? So pi 8 squared on 4, right? Which I'm pretty sure is 16 squared. Sorry, 16 pi. Yeah. So now someone can just type that in the calculator and give me the answer. 0.05. 0.05. Now, what is that unit? We go together like millimeters and megapascals.
Somewhere around.
Yeah.
Yeah.
The class last year, they preferred that way. Okay. This is a good question. All right. Right.
I just drew something that looked like
God damn it. Why did I not put in a singular grades?
Okay. Shh. Now, describe the process of hardening and tempering to produce a labeled sketch of the resulting microstructure in the circle. Now, I don't remember who it was. Somebody who they felt the need to correct my spelling and then forgot to label the drawing. It's like, I wish that you had just labeled the drawing instead of correcting my spelling. Yeah? Okay. Someone, describe for me the process of hardening and tempering.
Heat to austenitic range, then quench it in
Heat to
oil,
austenite,
brine.
quench in oil, serve salt bath, and then temper to like 400, 600 degrees, so 200.
Okay.
600. Yeah, for an extended range.
I will just finish this one question. Okay. So, great answers. Heat to the austenite range, or heat to gamma steel, then cool in oil, or quench in oil is a better word to use. Quench in oil, then temper. Yeah? After that, to draw the diagram, you just draw this, and you label it, and you say Martensite.
That's what we thought.
Now, I too once thought as you did. Now, I've learned from this paper that I clearly did not explain this to you. I remember hearing someone like Sergey say, "Oh, we have to draw Martensite. I've got that one. Like, I know how to draw Martensite." Yeah.
It's like so ready. I was like, fuck you,
Okay. I didn't know this until I started teaching this subject. It still looks like Martensite. Yeah, we just released some of the stress. Yeah? Hang around and I'll